Okay, so there is another theorem that says about the existence and uniqueness of a solution. But for this one, it's kind of stronger. But fortunately, the conditions for this theorem is kind of not that hard to get. So the second existence and uniqueness. The second existence and uniqueness theorem says that if we have a linear ordinary differential equation, so a differential equation that can be written as dy dx plus some function of x times y is equal to q of x, we call this kind of equation an ordinary differential equation. We call it an ordinary differential equation. This ordinary differential equation is linear, and first thing is first order because the highest derivative is first order. It's not like there's no second order differential equation, so there's no higher derivative. Only the first derivative exists here, first order. And we call it linear because this thing that is not multiplied by y, it's not a square, it's not cubed. Same thing for the other y. So it's a linear and differential equation because it's differential equation. So the theorem says if we have the b of, let's see the function, the coefficient of y, we call the function b of x, and we have another function q of x. It said that if both of them are continuous functions on an interval, and if we call this interval I, and we have an initial condition showing y of x is equal to capital Y, and x does belong to the interval, then we are guaranteed to have a unique solution. We guaranteed to have a unique solution. We have a unique solution in the interval I. So this is the theorem. The theorem says that imagine if we have, first thing, a linear differential equation. So we must have a linear. This theorem only talks about linear differential equation. First order, for now, first order linear differential equation. It tells you take the coefficient of f y and take the other function of x, which is q of x. See if those two functions are continuous. So we're gonna see if they are continuous in the interval. Which interval? And we're gonna ask ourselves, which interval are those functions continuous? If the initial condition that we were given lies in this interval, then we are guaranteed to have a unique solution in this interval. An example of this is y prime plus xy is equal to x. We ask ourselves those following questions. Let's ask ourselves these following questions. We have the function x. We take which interval is x continuous? It's continuous between negative infinity and infinity. For x equal to negative infinity to infinity. We have another x over there, which is again continuous from negative infinity to infinity. Imagine if we were given that y of 3 is equal to 2. Then according to this theorem that apologize, that there must be a unique solution over the interval between negative infinity to infinity. So there is only one unique solution because of the initial condition. Let's us have another example. This theorem is very easy. It's kind of introduction to things that we're gonna solve in the future. Because we're going to have a systematic way of finding the value of y. Another example of y prime plus 1 over x times y is equal to 2. So we have two functions here, which is 1 over x, which is v of x equal to 1 over x, which is continuous in either from negative infinity to 0, union from 0 to infinity. So we have two intervals that this 1 over x is continuous. This is the biggest two intervals. 2 is continuous from negative infinity to infinity. So once we come and take the intersection, the overall thing is continuous either from negative infinity to 0, union 0 to infinity. So based on the initial value problem, we can have different existence of uniqueness theorem. For example, if the initial value problem told you that y of negative 3 is equal to 2, then we are guaranteed to have a unique solution over the interval between negative infinity and to 0. The theorem does not say anything about x equals to 0. There may be no solution, and it does also say nothing about from 0 to infinity. If we have the solution of y of 4, if instead of having y prime of 3 is equal to 0, if we have y of 5 is equal to 6, then we can only talk about the existence and uniqueness of the solution in the upper interval between 0 and infinity. So this is another theorem of existence and uniqueness theorem, but that's only for first order linear differential equation.